Welcome to lesson 6.3, the binomial distributions. What are the conditions for a binomial setting? Remember to check your bins: binary, independent, number, and same success. So binary, the possible outcomes of each trial can be classified as success or failure. Independent, trials must be independent. That is, knowing the results of one trial must not tell us anything about the results of another trial. Look at the context to decipher this. Number, the number of trials n of the chance process must be fixed in advance. And the same success, there's the same probability p of success on each trial. So the count x of successes in a binomial setting is the binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p, where n is the number of trials and p is the probability of success on any one trial. The possible values of x are whole numbers from 0 to n. Note that binomial variables are discrete. Okay, let's practice one so we can make some context out of this. Determine whether the random variables below have a binomial distribution and justify your answer. Roll a fair die 10 times and let x be the number of sixes. Is it binary? Yes, because success is a 6, failure is not a 6, so we have an idea of success and failure. Independent? Yes, knowing the outcome of the past rolls doesn't provide additional information about the future rolls. Is the number of trials in the chance process fixed in advance? Number. Yes, there are 10 trials. We have that fixed in advance. Roll a die 10 times. And same success, is the probability p of success the same on each trial? Yes, the probability of success is 1/6. Always. This is a binomial setting. X is a binomial random variable with n equals 10 and p equals 1/6. 10 trials and probability of success. Shoot a basketball 20 times from various distances in the court. Let y equal the number of shots made. Is this binary? Yes, because success equals a made shot, failure equals a miss. Independent? This is not independent because the results of one shot do affect the next. Or you could argue it is independent because assuming making one shot does not change the probability of the next shot. Try to let your idea of independence reside on the fact that maybe there is follow-up questions and that it's relying on the fact that you are passing bins. Otherwise, on the AP test, they won't use something like sports and try to pass an independent test on that. Okay, so we could see this going either way. Number, yes, the number of shots is fixed in advance, and the same probability of success, no, because the probability of success depends on the location of the shot taken. That's a definite fail, okay? There is not the same probability of success because a shot taken from a deep, far angle on the side is going to be a lot more tricky than a shot straight on from like the free throw or closer. Okay. Observe the next 100 cards that go by and let C equal the color. Binary, no success is defined, so we can't say that there is a clear success and failure. Also, C equals color is not a random variable. Okay, rolling sixes. In many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1/6. If x equals the number of sixes in 4 rolls of a fair die, then x is binomial with n equals the number of trials 4 and p equals 1/6. If they go ahead and say x is binomial, then you don't have to go through the test to see if it's binomial, B-I-N-S, okay? They already said it is for you. Let S equal success and F equals failure. What is the probability that x equals 0? That is, what is the probability that all 4 rolls are not 6s? So the probability that one die is not a 6 is a probability of a failure, is 1 minus 1/6 is 5/6. There's 5 failures out of the 6 possibilities, rolling a 1, 2, 3, 4, or a 5. 5 ways that can happen. The probability of 4 failures is failure times failure times failure times failure, because we want to fail and fail and fail and fail. So ands we replace with multiplications, and we don't need to use we have independence, so we don't need to use conditional probability. So we can just straight multiply our 5 6s and get 0.482. So there is a 0.482 probability of getting no 6s in 4 rolls. What is the probability that x equals 1? That doesn't mean that you roll a 1. That means that you get 1 success. So probability of 1 success could be the first or the second or the third or the fourth success. So this can happen 4 ways. So your probability of x is the 4 ways that you can get 3 failures and 1 success. Okay, so that's 0.386. So what about 2, 3, or 4 successes? So 2 successes can occur in the first 2 places, in the first and the third, in the first and the fourth, or in the second, third, second, fourth, or in the third, fourth places. Okay, so how do you determine, especially if there's a lot more places something can occur and a lot more of them, how do you determine this value in the front of how many successes there are? So let's make a binomial coefficient that says n choose k. So we have n trials, like 4 trials. We're going to choose 2 successes. So 4 choose 2, 2 failures, 2 successes, okay, times the probability of 2 failures and the probability of 2 successes. 4 choose 2 is 6, and we see it right here. The first, second, third, fourth, fifth, sixth way that you can have 2 successes out of 4 trials. Okay, so there are 6 ways this can happen. 5 6 squared times 1 6 squared, multiply that all together, get 0.116. Okay, what about the probability of 3 successes? Out of 4 trials, have 3 successes. 1 is a failure, 3 are successes. So 4 choose 3 is 4, 5 6 to the first, 1 6 to the third. Okay, so let's go and figure that out on the calculator. So I'm going to go 4 math probability NCR 3. So that's 4 choose 3 gets you 4. Okay, and 4 choose 2, 4 math probability NCR choose 2 is 6. Okay, and that's how you get that first number in the very front. Okay, and 3 successes is only about a 1% chance of occurring, or a probability of 0.0154. And the probability of 4 successes happens one way when they're all successes, S, 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 and that's 5 6 to the 0 and 1 6 to the fourth, and that's 0.00077. So in general, how can we calculate binomial probabilities? We do trials times the number of successes, the probability of success to all the successes, the probability of failure to all the failures. Is this formula in the formula sheet? What is the most common mistake students make on the binomial distribution questions? On many questions involving binomial settings, students do not recognize that this is using a binomial distribution. In fact, free response questions about the binomial distribution are often among the lowest scoring questions on the exam. Make sure to spend plenty of time learning how to identify a binomial distribution. When you aren't sure how to answer a probability question, check if it's a binomial setting. In roulette, 18 of the 38 spaces on the wheel are black. Suppose you observe the next 10 spins of a roulette wheel. The big key to me of a binomial setting is that I'm not just looking for a probability of a event, or maybe just 2 events, like one then a conditional other or a tree diagram, okay? But I'm looking for 10 spins. Now this is dropping me into a binomial setting. So define x. Let x equal a spin that lands on black. X has a binomial distribution with n equals 10 and probability of a black equals 0.4737. So x is a binomial setting with 10 and 1838s, 10 trials and 1838s probability of success. What is the probability that exactly 4 of the spins land on black? So I want 4 successes out of the 10 spins. So I'm going to go 10 spins, choose 4, the number of ways 4 successes can happen. My 4 successes, probability of success to my number of successes, and probability of failure to the number of failures. So that's everything left, 20 out of 38, when 18 out of 38 is my successes, another 20 to add up to 38, and 6 to add up to 10. Okay, so there's all 10 trials, 210 ways that you can have 10 trials and have 4 successes. And then we get 0.225. Okay, so we go 10 math probability NCR 4 to do that part. What is the probability that at least 8 of the spins land on black? So probability that x is greater than or equal to 8. Now the underline matters because we have a discrete variable here. So probability that x equals 8, 9, and 10. So 10 choose 8 successes with 8 successes and 2 failures. 10 choose 9 with 9 successes and 1 failure. And all 10 successes. That is 0.0384. Or you can do the probability of 1 minus 7. Okay. So let's talk about binomial random probability. So you can also go second distribution, choose binom PDF or binom CDF. Now here's the cool part about this. You can just enter the number of trials, the probability, and the number of successes. So NPK is number of trials, probability, and number of successes. This computes the probability that x is equal to k, like having 4 successes out of 10 or 6 successes out of 10. But binomial CDF, instead of PDF, CDF computes the probability of less than or equal to that number of successes. So that would be a great way to use and figure out the probability that's greater than or equal to 8 is 1 minus the probability that it's less than or equal to 7. And then your calculator can give you this. All right, is it okay to use the binomial PDF and binomial CDF commands on the AP exam? Yes, but label your coefficients. Binom CDF, n equals p equals x value. How can you calculate the mean and standard deviation of a binomial distribution? And are these on the formula sheet? Mu x is np and sigma x is np 1 minus p. Yes, it's on the formula sheet. Use the number of 6's example to calculate your expected value the long way and then to reveal np. Okay. I'm going to skip that for now. Let x equal the number of the next 10 spins roulette wheel that land on black, where probability of black is 1838. Calculate and interpret the mean and standard deviation of x. So the mean is NP, so that's my number of trials and my probability of success. So if I have 10 spins and my probability of success is 1838, then I get 4.737 of those 10 that would be a success. And then for standard deviation, I want to go NP 1 minus P. So I'm going to go number of trials times successes times failures, and I get 1.58. So out of many, many times spinning 10 spins of the roulette wheel, on average, there will be about 4.737 black results. The number of times the roulette wheel lands on black after many, many times spinning 10 times typically differs from the mean of 4.737 by about 1.58 times that it lands on black. How often will the number of spins that land on black be within 1 standard deviation of the mean? So now let's try to figure out what the mean minus the standard deviation is and what the mean plus the standard deviation is, and so then we'll have the interval of 1 standard deviation within the mean, and we're curious how many times we can get a success within 1 standard deviation of the mean. So I'm going to break this up to look for the left area of the whole thing minus the left area of this, and then I'll have just that center area. So binom CDF, n equals 10, p equals 18 over 38, and x equals 6 successes, because that's the nearest integer here, minus binom PDF, n equals 10, p equals 18 over 38, and the number of successes is a 4, because if we say we have just a little more than 3 successes, then let's go all the way over to 4 successes, and then that will give us a smaller area in the inside, so it'll be a more conservative probability. So there we go. Binom CDF over here minus binom CDF here gives us 0.42. When is it okay to use the binomial distribution when sampling without replacement? And why is this an issue? Okay, so without replacement violates the independence condition, because as we're drawing from a sample, especially when we draw people and we're trying to collect a certain number of people, we aren't putting the people back to redraw their name again if they're already in our sample. So very commonly we draw, and other things too, we draw without replacement. But as I draw and draw and draw, my sample gets bigger, my population gets smaller and smaller and smaller, and it becomes more and more and more likely that I'm going to select these last people Okay, their chances are all going up for being selected. So do we have the same probability of success? No, on each trial, because everybody's probabilities that aren't selected are going up for being selected next. Okay, so without replacement violates the independence condition, but most real-world sampling is without replacement. So AP Stats and statisticians created this little caveat: as long as we sample less than 10% of the population, then we're okay. So if we had a population of 50, we could sample 5, okay, 10% of the population. A cereal company puts 1 of 5 different NASCAR cards into each box of cereal. Each card featured a different driver: Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, or Jimmy Johnson. Suppose that the company printed 20,000 of each card, so there are 100,000 total boxes of cereal with a card inside. If a person bought 6 boxes at random, now realize we're buying a lot of boxes, so this again is hinting us towards a binomial random variable. What is the probability of getting 2 Danica Patrick cards? Now realize we're also drawing 6 boxes without replacement, so therefore we need to test for drawing without replacement, drawing less than 10% of the population. Let X equal the number of Danica Patrick cards from 6 different cereal boxes. Make sure you start by defining your variable. Check bins. Is this binary? Yes. A success is Danica Patrick card, a failure is any other card. Check. Independence. Sampling without replacement is, so we are not independent, but 6 is less than 1/10 of 100,000, which is 6 is less than 10,000, so assume independence. Number of trials set in advance? Yes. N equals 6. And the same probability of success, probability is 20,000 over 100,000, which is 1/5. Okay, so X is a binomial random variable with N equals 6, the number of trials set in advance, and the probability of success is 0.2. Find the probability that X equals 2, that we get 2 Danica Patrick cards exactly. So we do 6, choose 2, 0.2 the probability of success to our 2 successes, and 0.8 the probability of failure to our 4 failures. That's 0.25 in the end, or binom PDF, N equals 6, probability of success is 0.2, and the number of successes is 2. There is approximately a 25% chance of getting 2 Danica Patrick cards out of 6 randomly selected cereal boxes. Okay, next up is a geometric setting. In this setting, we keep drawing until we receive a success. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get 1 success. On each trial, the probability P of success must be the same. There's no set number of trials in advance then. K is the trial that we get a success on, and we stop after the kth trial. The number of trials Y that it takes to get a success is in a geometric setting is called a geometric random variable. The probability distribution of Y is a geometric distribution with parameter P, the probability of success on any one trial, no N in advance, the set number of trials, and so the possibilities for Y are 1, 2, 3, and onward, because you can get a success on the first trial, a failure on the first, and a success on the second, or 2 failures on the first and second, and a success on the third. Monopoly. In the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that a player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1/6. Explain why this is a geometric setting. Let Y equal the number of trials it takes to roll doubles once. So we're going to check the acronym BITS. Binary, yes, a success is rolling doubles, a failure is no doubles. Independent, yes, die rolls have no memory, so they're independent. Trials continue rolling until this first set of doubles. So that's what we're going to do. We're going to change from bins, number of trials set in advance, to T, bits, which is just trials. We're just going to continue going until we get a success. And S is still the same as it used to be. Same probability of success. Yes, the probability of doubles is 1/6. Define the geometric random variable and state its distribution. Y is a geometric distribution with parameter 1/6. It is always right skewed. Okay. Find the probability that it takes exactly 3 rolls to get out of jail, exactly 4 rolls, and exactly 100 rolls. So the probability of 3 of y equals 3 doesn't mean 3 successes like it used to in a binomial random variable. In a geometric random variable, it means on the third roll you get a success. So we need failure, failure, success. So in this way, I also don't need a binomial coefficient in the front for all the different ways we can get one success or whatever, because we are only considering a success on the last roll. So therefore we have the specific order. So many failures up to that number, and then on that number we have one success. Okay, so 0.116. When y equals 4, then we consider 3 failures, so one less than that, 3 failures, and then the fourth one is a success. So fail, 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 success, multiply those probabilities in that order, and order specific for your work, I guess, and we get 0.09. The probability that it takes 100 rolls is going to be 99 failures and 1 success, and that gives us approximately 0. Okay, so in summary, we don't need that binomial coefficient of like n choose k in the front, because we're not taking like 100 rolls and taking just one success anywhere. We're taking that success in a certain spot. Okay, in general, how can you calculate geometric probabilities is this formula on the formula sheet. The probability that y equals k is 1 minus p, so the probability of failure, to the k minus 1, meaning like you're 99, not 100, but 100 minus 1 is 99, to your 99 times, and then the 1 time that you have the probability of success. Okay, so now we have Geomit PDF and Geomit CDF. Geomit PDF is for when your the number of trials it takes for a success is exactly equal to k, or if you're just looking for a success in some interval of trials, like will it take me less than 10 rolls or something like that. How do you calculate the mean of a geometric distribution is the formula on the formula sheet. Mu y equals the expected value of y is 1 over p. So therefore, 1 over the probability of success is essentially just inverting the fraction of success. So that's 6. So what does that mean? That means that the expected value, the number of trials that you're expected to take until you get a success, is 6 trials. This is not on the formula sheet. The expected number of trials required to get the first success is how it's interpreted. What shape do geometric distributions have? Graph the monopoly distribution from the first several successes of x. So what we're going to do is we're going to say the probability of doubles. The probability of doubles on the first trial is just 1/6. The probability of doubles in the second trial is 5/6 times 1/6, because you're going to multiply a failure then a success. And then third trial, fourth trial, fifth, sixth, seventh, eighth, and then figured out all the way to the 12th trial where there's 11 failures and 1 success. So if I was to take this and kind of just continue like ... I would have this of my number of trials until a success, and then the probability. Okay, and then this is the probability of doubles on this number of rolls. So if you got doubles on the first roll, it's most likely actually, and then the second roll it's a little less likely. Then not getting doubles until the third roll is a little bit less likely. Not getting doubles until the 12th roll is it's quite a bit less likely. Not getting doubles until the 100th roll, okay, is quite unlikely. Okay, in general, how many rolls should it take to escape jail in Monopoly? That is 6. If we were to roll 2 die many, many times, we expect the to roll doubles on average on our 6th turn. Okay, and probability that y is greater than mu y is the probability that your value of y takes longer than 6 rolls to roll doubles. That's 1 minus Geomit CDF with probability of success 1/6 and the success on the 6th one. Remember that CDF only works for a left area, so that means fewer than or equal to 6, but we want to know more than 6 rolls, so I have to go 1 minus fewer than or equal to 6, and that's 0.335, so there's a 33.5% chance that it takes you more than 6 rolls. Since only 33.5% of the data is above the mean, then the distribution shape must be right skewed. Okay, neat little interpretation there, and that's all for today. Thank you for joining me.